what is that? Algeria, and is going to Colombia. So a lot of these cyber attacks happens daily in the world. And therefore, this opened the requirement of improving the security of any transfer of information. So what is called information security. Nowadays, how you do this information security, use a technique that is called cryptography. So by cryptography, we mean the coding and decoding of a secret message. So the idea is that you modify the message as to make the content of the message unintelligible to anyone but the intended recipient. So in this way, what you do is that you take Alice sends a encrypted message to Bob, and Eve is not able to get the information that Alice is sending to Bob. Okay, so this is the goal of the information security. So in this case, so the goal is to try to create a very strong random key, random because in this way the others have no a low probability to guess the content of the random key, in order that this random key can be used to code your message so that the attacker is not able to get the information that you are sending. So this is the first point. And the second point is the fact that now you have to distribute this key between the user in a private way, so in a way that the others cannot intercept a key that you are sending. And so this is the goal of this first point, is the goal of quantum random number generator, and the goal and the approach that is used in order to face this goal is the one based on QKD, so quantum key distribution. So let us see how nowadays those two, generation of random key and distribution of the key, are actually implemented. Okay? So nowadays in any translation, transfer of information that you do, so what you are using the protocol of public key encryption. So with public key encryption, so what you are using is that you are using a pseudo-random numbers in order to encrypt your key and then render your information secure. So the basic principle of public key encryption is the strength of the mathematical algorithm that you are using. So here the idea is the fact that you are taking a key. This is the number that you want to send. This is the key that you want to use. You multiply the two together, and therefore here you get the crypto test. Okay, so the coded test. And so this encrypting is quite easy because it's simply a multiplication. However, if you want to decrypt the information that you are sending without knowing the key, this decrypting, so what is called here code breaking, is extremely hard, because what you have to do is that you have to factorize this number, and factorizing the number you have to find the factors. And this is quite complicated. And so therefore, so the security of today encryption is based simply on the fact that mathematics is complicated. However, there is a theorem that is the Shor theorem. There is an algorithm that is the Shor algorithm that is able to do this kind of factorization in an extremely short time by using a quantum computer. And so this problem of factorizing number can be quite easily solved by using a quantum computer. And therefore, once we will have a quantum computer, people are saying our system will break. So you see, these are a few announcements on the newspaper that say quantum computer pose imminent threat to Bitcoin security. So you can decode the Bitcoin. Scientists can claim blockchain-based products are at risk of attacks from quantum computers. So also the blockchains can be broken. And therefore people say, oh, we will face what is called a cryptography apocalypse. So everything destroyed. Quantum computing, how to address the national security risk, because the quantum computer can intercept and can be able to decode everything that we are trying to render secure. And so this is quite a severe problem. How can we face these difficulties? So we can face by using different cryptography approaches. So one cryptography approach is called a quantum breakable approach, meaning that in this encryption approach, if you have a quantum computer, you can break those approaches. Other approach are called quantum secure approach. And therefore, there is the National Security Agency of the USA that has proposed a series of approaches that is called quantum safe. Are they really quantum safe? Not. Okay? So those quantum safe approach are called post-quantum cryptography approach, meaning those approaches that are able to maintain the security even in presence of a quantum computer. So those approaches are called the post-quantum. So NSA has published a series of what they call quantum safe approaches, and after a couple of weeks, people have been able to break even those quantum secure approach. And therefore, quantum cryptography protocols based on algorithm, based on software, are not secure. And so the idea is to use not post-quantum approach, but to use quantum cryptography in order to have something that is really secure. So here the issue is, how can we make a key that is able to be extremely random so that no one is able to guess our key? So let's see about how can we make a quantum, how we can generate a random number. In quantum mechanics, so we can generate the quantum number quite easily. Okay? So we take one photon. We know that the photon through a beam splitter, so we have already discussed this several times. We know that this photon, when it's arriving in these beam splitters, has 50% of probability to be transmitted and 50% of probability to be reflected. And therefore, there is 50% of probability that this detector clicks and 50% of probability that that other detector clicks. But since we have a single photon, physically, actually, what happens is that while doing measurements, we know that either this detector click or that detector click. And therefore, in this way, so if we say that when this detector click, we have 1, and when this detector click, we have 0, so we have a sequence of 1 and 0 that cannot be predicted because we don't know where the wave function of the photon will collapse, but the 0 and the 1 will be produced with an equal probability, 50%, 50%. And so the sequence of clicks give us our random number. So the question is this experiment, quantum experiment, different from tossing a coin? You know that the way that we can use in order to make a random number is simply toss a coin. If it is head, is 1, if it is crux, is 0. So the question is, are the two different or not? According to you, are the two different or not? Are the same? No, they are different. Why? Because the randomness in this case is based on our not knowledge of the exact condition by which we are tossing the coin. So this is classical mechanics. You know that in classical mechanics, Newton law say that if we know this initial condition, we can predict how a system evolves. And when Newton say we can predict, it means that we can predict with 100% of certainty on the result of the evolution of the system. The problem is knowing the initial condition. And indeed, so when you toss a coin, so you don't know exactly how you toss the coin, how the coin is placed on your finger, how you throw the coin high, how the coin interacts with the atmosphere, how it arrive on the ground, and so on and so forth. And this limited knowledge of the condition through which the coin is moving give you the statistical uncertainty of the results, which tells you that the result of the tossing of a coin is unpredictable. However, there are people that did experiment. So here is a paper by which they carefully control everything, all the starting condition, and then they got the results that each single tossing of the coin can be exactly predicted. Even more, so there is a family that is the Peleus family that were able to break many Vegas and many roulette in Spain without any trick, but simply observing how the roulette were fabricated and how the spinning of the roulette was affected by the physical roulette that they was using, and then they got millionaire because they were able to predict the result of a throw of the roulette in several casinos. So they were able to earn a fortune through casino games. People were trying to sue this family by saying that you are using some illegal means in order to understand, in order to predict the result of the roulette, but indeed at the end, so they were able to prove that the only ingredient they were using was simply the observation and the know-how of how the roulette was working. And so therefore, so the difference between a quantum experiment and the tossing of coin is significantly different. So in this case, so the result is assured by our unknown of the starting condition. In this case, so the result is assured by the knowing of the theory that we can describe exactly of what is happening. So this is essentially the base of quantum approach for cryptography. Okay? And so there are many applications of quantum cryptography, and here is the prediction of the amount of millions that a quantum cryptography market will face. You see that the increase in the quantum cryptography market is assumed to be significant, and therefore, so what we did was to try to use some quantum mechanism in order to make a random number generator. So this was our first approach. So this is how we can make a quantum random number generator, so a generator of random number based on a quantum mechanism. So our goal was to make something that is cheap, is compact, is CMOS compatible, can be integrated into any device. And so the idea, so those are the people that worked, so Zara Bisadi, Giorgio Fontana, Niccolò Leone e Stefano Azzini in my lab that were working on this approach. So the idea here is why don't we use an LED? And we use an LED as a quantum source of randomness. So since the emission in a semiconductor is a spontaneous emission in a semiconductor is a spontaneous process, it happens that when a photon is emitted is an unknown quantity. And so if now we measure when the photon is emitted, we can generate it, since it's unknown, is a probabilistic process, we can generate it random numbers. So the idea was simply to do an experiment by which we have a voltage source, a silicon LED, a single photon avalanche detector, so we need to count the single photon, and then a multi-channel scaler, and then a PC. Okay? So the idea is that, so we drive the LED emits a photon, a single photon avalanche detector click, and then by measuring the time at which this click occurs, we have a sequence of random numbers. 0, 0, 1, the photon has been emitted, 0, 1, and so on and so forth. So the principle is very simple, so we did the experiment, and this is the result of the experiment. So this is the probability as a function of time of measuring a 0 or a 1, and we see that, for example, if we look at the probability of measuring 1, we see that we have that the probability of measuring 1 is 50%. So we don't know when the 1 occurs, but the probability is 50%. So then we use this source in order to see whether the source was actually a random number generator. So there are tests that you have to be able to pass in order to prove that your source is a random number generator. So the results of your generation is truly random numbers. And so this source, based on a very simple process, passes all those tests. So this was nice. So we try now to move to another approach. And what we tried to do now was to move from a macroscopic setting into a very tiny setup. So what we did here is that we have that the source is on a wafer and the detector is a commercial device. So then we move to two chips that we fabricated in collaboration with the Bruno Kessler Foundation. So we have the source and the detector, then we bonded together the source and the detector, and finally we integrated both the source and the detector within the same chip. Okay? So this is the cross-section of the integrated chip. So the circuit is completely a CMOS circuitry. So what you have here, you have a silicon LED, nothing else than a PN junction, forward bias. Here you have a silicon avalanche, a single photon avalanche detector, so simply a PN junction in an avalanche regime. And here you have integrated some logic that is used in order simply to count the photons that are indeed emitted. So this is the geometry which we end up. So you see that everything is in a very tiny integrated circuit. You have the silicon you have the silicon emitter, you have the SPAD, you have the silicon emitter, you have the silicon SPAD. Everything is integrated. You bias the system opportunely, and then you have your random numbers. So you compare the random number generator. You compare the random number with the different suite that tells you whether you are indeed generating truly random number, and the result is that all the tests were successfully passed. The random number was able to generate numbers at 1 gigabit per second. So we were very happy, and we developed a very compact system. So this is the system that we developed. So here you have the random number generator. Then everything is integrated on a board. So then we deposit a patent, and we started to consider to commercialize, so to start to found a startup in order to commercialize the device. So the story looks like a good story. Unfortunately, at the very same time, there was another company that is ID Quantique, so it's a Switzerland company that was commercialized a system that is very similar to what we developed. And so this means that our startup was not at the end founded. So those QRNG, very integrated, very small chips, are indeed deployed in the market. And here is an example of one company, Samsung, that is integrating in their smartphone this quantum random number generator that are developed by ID Quantique. Okay? So the story here is that you need to reach the results before the others, but at the right time in order to be able to get a market opportunity. So here we were lucky. We were unlucky because we were late. Now what I want to try to discuss is another approach that we follow in order to make this quantum random number generator. Now what we want to do is that we want to exploit the fundamental properties of quantum mechanics. One properties that make quantum mechanics different from classical mechanics. So any suggestions? So if you want to use the fundamental properties of quantum mechanics, which one you would use? Any suggestion? Let me see if you have the same idea that we had. What you will use? Which properties in quantum mechanics we will use in order to make a random number generator? So what is the strongest properties that differ quantum mechanics from classical mechanics? No idea. Entanglement, correct. So what we try to do is that, why don't we make a quantum random number generator that is based on the entanglement? Okay? So how can we do that? For example, so we take an entangled photon pairs. So people was complaining about QKD, so here is an example of. So we take an entangled photon pairs, then we prepare our entangled photon pairs, and then we do the measurements. Okay? We don't know where the wave function of the entangled photon pair will collapse. And therefore, since we don't know where the entangled pair collapse, we can get, by post-processing, we can get a random bit sequence. So, for example, this is an entangled photon pairs, which is characterized by a direction and by a polarization state by, where is it here? No, you remember. So we have that the wave function of the entangled photons, C, is equal to 1 square root of 2 of 0 V plus 1 H horizontal. H. Okay? So this is one photon in the vertical polarization state. This is the other photon in the horizontal polarization state. But we don't know which one of the two is the one that is going to arrive here. So we make a polarization filter there, and so we can screen. And sometimes we get 0V, sometimes we get 0H. If 0H, we don't get any click. If 0V, we get a click. And this is quite powerful tools, because since the two are entangled, when here we get 0V, there we get 1H. And therefore, so we have that in this way, we can send the same random key to one entanglement. So a property that is reflecting the contextuality, the entanglement, but more stringent properties, that is the contextuality of quantum physics. So which are the 2 degrees of freedom that we want to use, that we are going to exploit as a resource in a single photon? So here the idea is to use a single photon which has 2 internal degrees of freedoms. And what we are doing is that we are entangled together those 2 degrees of freedom. These are the collaborators, so Sonia Mazzucchi, Walter Moretti, Nicolò Leone, come si chiama questo? I forgot the name. Matteo Pasini, now I remember, and Davide Pastorello. Okay, so those are people in my lab. Walter Moretti is in the mathematical department. Sonia is a professor in the mathematical department. So those are in my lab. So here we do together this development. And so here the idea is to have a single photon with 2 degrees of freedom that are entangled. What are the 2 degrees of freedom that we are going to exploit? One is the polarization, easy. We already know. So the vertical and the horizontal polarization. And the other one is the direction, so the momentum of the photon. Whether the photon is going up or whether the photon is going down. Okay, so those are the 2 degrees of freedom. So let us see how we produce this entangled photon state. So it's very simple. So you start with a laser, but you can start with any light source. Let's say that we start with a photon here. Then you fix the polarization state of the photon by using a polarization filter. And then you fix a direction. Let's say that this direction here, so the direction, the horizontal direction, we call 0 direction. Okay? And so this is the momentum of the photon. Okay? So the photon is traveling straight. And so here we have a very well-defined photon state. So we have a photon that is traveling straight and that is characterized by a vertical polarization. Then we add a polarization beam splitter, meaning a beam splitter that, depending on the degree of polarization of the light, is sending the light upwards or in the straight direction if the polarization is vertical. And so therefore what happens is that we have that our single photon has a 50% of probability to go there or 50% of probability to go there. So after the polarization beam splitter, what we have is that our single photon is in a superposition of 2 states, of 2 momentum states, where the photon is up or where the photon is going straight. And so in this way, by using the polarization beam splitter here, so what we have end up is with a photon that is in a superposition of 2 states. This is not yet still an entangled state. Now what we do, we rotate the polarization state of the photon that is traveling in the straight direction by using a polarization rotator. And in this moment, so we have an entangled photon state, so a single photon that is in entangled state between the photon that is traveling in this direction and has the vertical, where is this one, and has the vertical polarization, and the photon that is traveling in this direction has an horizontal polarization. So in this way we have generated a single particle entangled state. So a photon that is an entangled state between 2 degrees of freedom. Can we use this for making a quantum random number generator? Yes. What we do is that we need to project the photon state into the different bases in order to measure the actual state of the photon. But before that, we need to prove that indeed, in this case, we have an entangled state. And to measure whether we have an entangled state, so there is a test that is called the Bell test, which, if violated, show that the photon is indeed in entangled state. So this Bell test is a quite simple test by which you assume to have 2 measurements set, so 2 rotation of the photon states. And then now you rotate over all the possible photon states, all on the basis of your photon state, and you can get 4 possible outcomes, whether the photon is moving straight, whether the photon is moving upwards, whether the polarization of the photon is horizontal, or whether the polarization of the photon is vertical. So for any projection of your photon state, you have 4 possible outcomes. Then what you do, you measure the correlation function, And then you end up with a sum of the different correlation function for different measurement set. And this number here is S. And Bell say that if S is larger than 2, then you are violating the Bell inequality. But if you are violating the Bell inequality, then the quantum mechanics is correct, your system is an entangled state, and then you can use the unpredictability of the quantum mechanics. So then we did the measurements. So what we did was indeed to change the different, so to project our photon state on the base state. So we changed this angle here, and we perform the measurements of this S parameter. And what we do observe is that for given projections, so we are able to violate the Bell inequality, meaning that we indeed were able to produce entangled states. And what is quite important here is the fact that we were able to prove the violation of the Bell inequality both by using a laser as well by using an LEDs. So here is the result with an LEDs. So moving from a coherent source to a spontaneous sources. And this is quite important because a laser is much more expensive than an LEDs, and therefore if you want to make a product, you can make a product by using a low-cost sources. So then we perform the experiment. We mount on the table our generation state. So here we form the entangled photon states. Then we project the entangled photon states on all the different bases. And then we use 4 detectors to do the measurements. And so this detector is measuring only the photons that are coming from the upward direction and has an horizontal polarization. This detector is measuring the photons that are coming from the upward direction and have a vertical polarization. So this photon is measuring the photons that are traveling in the horizontal direction and have an horizontal polarization, and this detector is measuring the photons that are traveling in the horizontal direction and are measuring and have a vertical polarization. And therefore what we are doing, we are looking at all possible combination. We are looking at all possible combination of our entangled photon state. Is this a quantum process? Yes, because we measure the violation of the Bell inequality. Is the result random? Yes, because quantum mechanics tell us that we cannot predict a priori which one of these 4 states can be actually measured. How can we do to transfer the result of the measurements in a sequence of random numbers? So this is quite easy, okay? So we do assign a label to each detector, and in case it's the detector 0V that clicks, we have a sequence of 0, 0, 0. If it's the detector 01, we have a sequence of 01. If it's the detector 1V, we have a sequence of 10. If it's the detector 1H, we have no, this is a bad result. We have a sequence of 11, okay? And so it happens that now, by knowing which detector counts, we can generate a sequence of random numbers. And the randomness of this sequence is assured by the quantum mechanics. What are the advantages of this technique? The advantages with respect to other technique is the fact that we can use a simple, cheap light source. So you see the kind of light sources that we were using, an LEDs, which you have in any lab, okay? It is very cheap. So an LED costs less than €1. So extremely cheap technique. What is the disadvantages of the approach is the fact that we need to have a very huge tabletop experiment. And since it is screened by light, everything is placed into this big box, so we call this setup the piano. Okay, you know the pianoforte, so the music instrument looks like that when it is open. But typically it's closed. Even also the pianoforte can be used closed. So everything is closed because we want to screen the system by any photon that is coming from the ambient. The problem is that this is not integrated circuit because it's square as a dimension of a square meter. And so then what we did was, since we have proved that the randomness is quantum, so the question is, how can we integrate the system in a millimeter square chip? And so we started to do some design effort, and we end up with a very compact design. And so we were able to integrate this meter square experimental setup into a very tiny quantum circuit. So this is the quantum circuit that we are using. You see that here we have optical fibers that are coupled to the quantum circuit. Everything is bonded is mounted on a PC board. The reason why we have a PC board is because we need to insert and extract electrical data, so electrical current into the circuit. So everything is very compact and can be prone for the application. So the question is, how can you now generate a single particle entangled state in a circuit? Any idea? So how can we manage the qubit in a circuit like this one, like this? Any idea? So what we are using is path encoding. So this is quite a common technique in integrated quantum photonics. So instead of encoding the information on the photon, you encode the information on where the photon is propagating through. And this is called path encoding. So for example, in this case, you have 4 waveguides, and the qubit is where the photon is actually propagating through. Okay? So now let us see how can we get 2 degrees of freedom for our photon by using 4 different waveguides. So the first degree of freedom, which resembles the momentum degree of freedom in the experiment I've shown you before, is whether the photon is in the waveguides that are in the down plane or the waveguides that are in the upper plane. So that means that we have 4 waveguides. We have a symmetry plane here, the white dashed line, and we have the 2 waveguides are on the left of the line, and 2 waveguides are on the right of the line. Okay? And so what we say is that, so the first degree of freedom is whether the photon is in the upper plane or whether the photon is in the down plane. Okay? We have a single photon, and the photon can be either here or there, or the photon can be here or there. And this is our first degree of freedom. Then now we need a second degree of freedom that resembles the polarization degree of freedom. And so this degree of freedom is whether the photon is in the waveguide that is near to the dashed line or whether the photon is in the waveguide that is far to the dashed waveguide. And therefore now we can have 4 different qubit states. Okay? So we have 4 different qubit states. So the first state is the upper state. So the photon is in the upper plane. The second state is the down state. So the photon is in the down state. So then we have another state that is far state. So the photon is in a waveguide that is far from the dashed white line. And then we have another state that is the near state. So the photon is in a waveguide that is a near state. Okay? So now I have 4 waveguides, 1, 2, the symmetry plane, 3, and 4. Okay? And now I put a photon in here. So if I put a photon in this waveguide, so I have a state that is described by the fact that the photon is in the upper plane times the photon is near waveguide. So then this state is nothing else than a state that I can call upper and near. Okay? So then I put a photon in this waveguide here. And so now I have a photon that is in a state that is characterized by the fact that it is in the down waveguide and is in the far waveguide. And so this photon here is in a state that is labeled by df. And so you see that here I have 4 states that are described by the product between the degree of freedom far and near and the degree of freedom upper and down. Okay? So this is the resource that I'm using. Okay? And so I have that when the photon is in the first waveguide, I have an upper far state. When the photon is in the second waveguide, I have an upper near state. When the photon in the third waveguide, I have a down near state. When the photon is the fourth waveguide, I have a down far state. Now I need to generate the entangled state. How can I do that? Simply by using this integrated circuitry. Okay, let me get an input waveguide here. Let me draw the symmetry plane there. And now I do have a waveguide that is far and in the upper plane. And then here I have a waveguide that is down and near to the symmetry plane. Okay? And therefore now I'm inserting a photon here. Inserting the photon here means that I'm starting from a state that is upper far. Then I have the beam splitter. What is making the beam splitter? The beam splitter is making a superposition of my photon state between a far and a near state. Okay? Then I move the photon from this position here to that position there. And now what I'm doing is that I'm getting an entangled single photon state between upper far and down near. Okay? You see that if I'm looking at what happens here, I have that the wave function that is describing the state in this plane here is equal to a superposition between a photon in the upper far waveguide plus a photon in a down near waveguide. I have realized an entangled photon state. I don't know where the photon actually is, but is in a superposition of a photon in the upper far waveguide and a photon in a down near waveguide, which is exactly the same initial state that I've used in the piano. Okay? And so now I have a single particle entangled state, and I can try to use this single particle entangled state for my quantum random number generator. So the first thing is that now I should have the possibility to change the probability, so to project my actual state over the upper-down basis or over the far and near basis. So I have to change the probability in a continuous way between a photon that is in the up and a photon that is in the down waveguide. How I can do this projection? Very simply by using a Mach-Zehnder interferometer. So if I'm using a Mach-Zehnder interferometer that in the chip is made by using an MMI, so a beam splitter, 2 phase shifter and another MMI, So what I do get is that if I'm starting with a photon in a given state, which can be the upper, the down, the far, or the near, I do make the photon travel through the Mach-Zehnder interferometer, and at the end, I have a superposition of a photon that is in one waveguide, for example, in the upper waveguide, and a photon that is in the low waveguide, for example, the down waveguide, and the amount of probability of percentage of this photon that is traveling in the upper waveguide or in the down waveguide is weighted by the phase shift between the two phase shifters. And so what I do get with the Mach-Zehnder interferometer is the fact that now I'm rotating in a continuous way the photon state between the qubit U to the qubit D. Okay? So this is a continuous projection of the photon state along all the possible states between 0 and 1. So I'm going to integrate all this rotation within the circuit. So in this part here, what I'm doing a rotation in the relative position degree of freedom. So you see here I am in a near waveguide, and after the Mach-Zehnder, I have that the photon is spread between a near waveguide and a far waveguide. Okay? So this is the rotation in the far and near degree of freedom. Then I need to do a rotation in the upper and down degree of freedom. And therefore, in order to do that rotation, so I take here this photon, I move the photon here, there, I reach this Mach-Zehnder, and then I'm sending the photon either in the upper plane or in the down plane. Okay? And so in this case, what I'm doing, you see, I'm getting a photon in the upper plane, zoom, zoom, zoom. Through the Mach-Zehnder, I send the photon either in the up or in the down plane. Okay? And so I get a rotation in the upper and down plane. And then I need to rotate also the other half. And so here I get a cross and I do the rotation. Here I'm enter, I cross and I do the rotation. Here I enter, I cross, I do the rotation, and so on and so forth. And therefore, what happens? At the end, I have 4 different outputs, and those 4 different outputs are now able to measure whether the photons was in an upper near state. Why I do have here the upper near state? Because you see that I'm moving from a near state to the upper state, and therefore this was initially in the near state, you see, and therefore this is labeled upper near, or in a upper far, so we go back, we are upper far, or in the near far, down far, sorry, so I go through, down far, or in the down near, so I go through, and I am in down near. And so in this way, by using this structure, I am entering here, I'm generating my entangled state there, and then I'm measuring where the photon at the end of the projection is actually collapsing. And so I can do a rotation. So the first thing that is quite interesting in this chip structure is the fact that I can operate the chip by using commercial LEDs without any problem, very low cost. All the components here are linear components, and I'm no longer interested in the time of arrival of the photon. So I'm simply interested in clicking. And this is quite powerful with respect to alternative approaches. We discussed yesterday the fact that in an entangled state, I need to synchronize the moment. If I have 2 particles, the moment I'm doing the measurements. Here I don't care, because I'm doing entangled state by using a single photon. It's also robust with respect to losses, to polarization mismatch, to everything. And I can do the experiment in a very simple lab. So this is the actual lab that we are using. So those so this is the chip, the fiber. You see the fiber are reaching this point where you have all the detectors that clicks when the photons arrive in the appropriate detector. So I can do the measurements. I can verify that indeed the results do violate the Bell inequalities. So this is the Bell inequality measured by using the LED in our experimental setup. You see that the result of the S parameter is larger than 2 here, is larger than 2 there. And therefore now if I'm sitting here in this condition of the circuit, I can do the experiment, I can collect and see whether it is the detector number 3 that click or the detector number 2 that click. Then I translate the detector number 3 in the binary numbers, and I have a sequence of binary numbers that are randomly assured by the quantum mechanics. So this is nice, this is working. So we were happy of that, and therefore we tried to start a spin-off company, okay? So we had a logo, so the university approved the formation of our startup. So this company is called SPECI, which means single photon entanglement for quantum key distribution. So we found the startup, we went to the venture capitalists and we say, why don't you give us some money? And they say no. And we asked, why no? And they say, because no one believes in quantum key distribution nowadays. And therefore the company was not founded. So the venture capitalist said, so if you would have come 5 years ago, we will have gave to you a lot of money. But we were late. So the story here is, I have shown you 2 times the story. In the first case, we were late because a competitor was already introducing the device on the market. In the second time, we were late because the market was not ready at that when we proposed our product, was not ready to support the product. So here the story is that you don't need to have, only need to have a bright and a very competitive technology, but you need to arrive on the market in the right time. Okay? So there are many other examples. So these are simply our example, unfortunate example for us. But there are also many other examples that show that the success of a technology is not only due to the technology itself, but also to the readiness of the market to valorize the technology that you are proposing. This was for us unfortunate from the point of view of the market opportunity, but not from the point of view of the academic opportunity, because so we were able to write a couple of papers and then the people got their PhD or whatever. Okay? So then, if you are interested in the slides, so here is the link where you can go and then download all the slides. I think that okay, you have already. Yeah. And in this link, so you will also find slides, presentation that I had no time to give on neuromorphic photonics, I guess also on QKDs and things like that. And at the end of the story, at the end of the day, I would like to thank you for the participation in this course. I finished. Question? Yes.
Sir, in one of the graphs, it was mentioned that H minimum should be less than 40%. That means, I just want to clarify once, that means randomness involved in random numbers which are generated, right? What does that H min mean? That's what
yes. This is a very good question. So if you are interested in the details, so there are some very complicated paper that discuss this concept of the H minimum. So you can go in this paper here, entropy certification of, or you go through this paper, where is? I have not listed here. So a strongly mathematical content paper where you saw. So H min, in a way, is the minimum entropy that is associated to your random number. So that means the following. Entropy means how much random are your numbers. And the minimum number of H is what fraction of your random number is truly random. Okay? When you say that you have an H min of 40%, it means that out of 10 numbers that you have generated, only 4 are truly random. Okay? So that means that the knowledge of the 10 bits allow you to guess the next bit that is generated with a confidence that is 1 minus H min. Okay? And therefore, people what are doing are distilling the random numbers at a level where H min is equal to, whether the entropy is equal to 100%. So in our case, we have 10 bits, H min 40%, so we have to discard 6 of those bits. And we end up with only 4 bits that are truly random, meaning that by using those 4 bits, you cannot guess the next 5th bit in a sequence. And so the larger is the H min, the more the entropy is present, so disorder is present, randomness is present in your bit sequence, and the more bits you can actually use. Okay?
So in that case, how can we increase it?
Very good question. So how can we increase? So the value of H min is essentially dictated by the non-ideality in your system. So anything that departs from the ideality in your system decrease H min. So in a purely ideal system implementation of the scheme that I propose you, so the H min will be 100%, because quantum mechanics is probabilistic in nature. So if everything would have been perfect in this experiment, maybe this one is easier. In this experiment, I would not be able to say in which one of those detectors will click. However, you have imperfections. For example, you may have that the losses along a path is slightly different than the losses along another path. And so that means that the probability, so if here I have larger losses, and here I have lower losses, it means that the probability that this detector clicks with respect to the probability that this other detector clicks is lower. And therefore, the randomness is no longer assured, because I know that I will have more clicks from here than there. And so I can predict the next click, because if one detector has a larger probability to click, it means that the other detector has lower probability to click, and therefore 0, 0 is present in my sequence with a larger probability than 1, 1, for example. And so the imperfection affect the value of H min. Then I do have, so I say the losses, I do have the unbalance of the Mach-Zehnder. In my description, I was assuming that this MMI here is 50%. Okay, 50% there, 50% there. But when you actually produce the MMI, so you may have an imbalance between the two arms of the MMI, meaning that instead of 50-50, you have 49-51. Okay? And this is also affecting the randomness, because you are saying that you have a larger probability to get 51. Okay? And then you have the rotation here of the Mach-Zehnder. Okay? If the phase is not exactly the one that I was supposed to get, I'm trying to project, so to make a rotation of this angle, instead of this angle, I get another angle, and so on and so forth. So any imperfection in the device reduce the value of H mean. Okay? But I should say that 40% in H mean is an achievement, meaning that in the first device that I've shown you, the H mean that we were able to get was of, I think, 20%. So here in integrated photonics, so we are getting rid of any misalignment which we can get with microscopic element, like in the piano, and where we had a lower H mean.
Thank you, sir.
Sir, that also generation rate is in kilohertz, 50 kilohertz only. And we are thinking about high-speed quantum communication.
Okay, yeah, so the question is, why the generation rate is 50 kilohertz, okay, instead of millions? So this is essentially due to the fact that here we are using SPAD, silicon SPAD, as photodetector. So the dynamic range was limited.
So if we use SNSPD, then it will work better?
Yes, if you use, yes.
Okay.
And then the second question is the fact that we need to be sure to have a single photon, okay? And then where was the example here before? And this is not assured if you use an LEDs. So we are not using a single photon sources. And therefore, what happens is that there is some time where you have the two detector clicks at the same time. And if the two detector clicks at the same times, I have to discard this measurement. Yes. And therefore, so this is also limiting my my rate. And finally, the problem is the LED. So the photon flux that is generated by the LED. So I'm using an LED, cheap, low cost, blah, blah, but the power emitted is much lower because it's emitting everywhere, is not co-emitted. And therefore, I would need to have a watt, an LED that is able to emit a watt of optical power to really input in my circuit a very high flux. But if I have many photons, I need to have very fast photodetectors, okay? Because otherwise, in a single observation interval, I do measure two events, okay? So here I'm okay, I don't find. But here I am limited on the temporal resolution of the detector, the dead time of the detector, and so on and so forth. So the detector is limiting the bit rate.
Okay. Thank you, sir.
Sir, I have a very basic question. Actually, we can define the phase.
Okay. While if you are considering a single particle, you are asking, so what is the meaning of the phase in this single particle? However, what we are dealing with are not the single particle, but are the probabilities that the single particle is in a given path. And therefore, so what we are considering are the probability associated with the particles. And the probability are described as a waves. And so I can have a phase difference between the two probabilities. And that means that, for example, in a Mach-Zehnder, and this is the reason why we are using the Mach-Zehnder, I can project, okay, so this is a projection, and when I'm writing this, is nothing else than I'm writing the probability of having the photon, okay, in that specific waveguide, okay? And therefore it is in the probability, because the probability wave I'm considering, no, the wave function. So the probability wave, so in the probability of having the photon in that specific waveguide is the one that is affected by the phase shift. Do I have answer? So it's more clear now? Okay? And so by changing phi1 and phi2, I can have a probability equal to 1 or a probability equal to 0 there. I change, I increase the probability, I decrease the probability, And therefore, I'm projecting the photon with a given probability here or there. If I'm looking at the photon, I'm doing a measurement, so the wave function of the photon will collapse. And then I will have either the photon here or there. I do the measurements with 10 photons, and I get that if this probability is 30%, I get out of 10 measurements, in average, I get 3 photons here and 7 photons there. Okay? So this is a probability.
So you are saying like with respect to phase shifter, whatever phase change is there, that is the affecting the probability of photons in which area it will be there, right?
Yes.
So in terms of wave theory, we cannot assume like this is phase shift.
In terms of filtering, you mean?
Yes, sir.
Filtering in terms of.
Okay.
Now, what is the question?
So you are saying that with respect to phase shift, we are changing the probability level of photons, right?
Yes.
Okay.
So it's the probability wave that is following the photon that while he is traveling. Is the same what we are doing here, okay? Also here in the Mach-Zehnder, in the MMI, so when I was saying that we have 50% of probability to have the photon there and 50% probability to have the photon there, so it means that I'm dealing with the probability. If I'm looking the single photon, so a single photon will be either here or there. But if I'm considering the probability, I have a superposition of the two states where the photon is both here and there. It's like with a Schrödinger cat. If the box is closed, I have the superposition, a given probability, of the cat to be alive or dead. But if I'm looking, I want to know exactly what is happening, so the cat is going to be either dead or alive. And here the same. So if I'm not measuring, I do not force the collapse of the wave function on a given waveguide, and I have 50% of probability of having the photon there and there. And so I make that if I want to describe where the photon is, I have a superposition of the state, the photon here and there. But if I'm doing the measurements, I will get either the photon here or there. So this is the difference between the collapse of the photon, so doing the measurements, or the probability evolution of the wave function associated to the photon state. Clear? Thank you.
Sir, one more question. Sir, I have come across so many words while reading the papers, but I did not have an exact, so I just want to know that difference between quantum random number generator, then Gaussian random number generator, then GRNG, Gaussian random number generator, then somewhere pseudo random number generators.
See. So the difference, okay, so you have so the random number generators are essentially a pseudo-random number generator. They are essentially based on algorithm. Okay? Then you have physical, so pseudo-random number generator. Then you have physical random number generator, and those are based on physical mechanism, physical processes. And then you have that a subclass of those are the QRNG, where the physical process is a quantum mechanical process. And how do you ensure the security or the randomness? So here in the algorithm is the computational power that you have available that guarantee you the randomness. And these are the field of post-quantum, quantum, cryptography. So that means that we want to develop algorithms that are so robust that even with a quantum computer you cannot break. Okay? And this is quite tough because, as I will show you, NSA, so the National Security Agency of the US, published a list of post-quantum approved algorithms, and after the publication, a couple of weeks after, two Danish computer scientists, I guess, were able to break the code. Okay, and so here is essentially the robustness is ensured by the computational power that you put in order to make the algorithm. So you take two big random prime numbers, you multiply those big prime numbers together, and then you preserve only a fraction of the resulting binary numbers. And this is your random numbers. Or, on the other hand, you have those that are based on physical processes. So you toss a coin, or you measure the noise in the current that is flowing into a resistor. Now in the computers, so you have random number generators that are based on the shot noise of the current that is flowing in a resistor, in a circuit that is integrated in the processor. And then based on that, so they do generate random numbers that you use when you do the calculations. Okay? So these are physical-based random number generators. What is the problem with the physical-based random number generator? The problem is associated to the fact that if you know everything, so you are able to predict the next number, as in example of tossing a coin that I did. In the case of the quantum, so the security here is provided by the fact that by our limited knowledge of what is happening inside the resistor. Okay? But if we know exactly all the distribution of the carbon grain in a carbon-based resistor, the distribution of all the carbon grain, we know exactly how many electrons are entering, we know exactly where the electrons are moving through, we can predict the noise and we can predict the random numbers. Okay? So this is the base of the physical random number generator. But if the physical process is a quantum mechanical process, we are ensured that if the system is ideal, and not if we have limitation on the fabrication of the system, if the system is ideal, so there is intrinsically in the nature of the quantum mechanics that we cannot predict how the wave function, in which specific state the wave function will collapse. And so in this way, so we can use this mechanism in order to generate random numbers. Okay? But we need to be sure that the mechanism that we are using, the physics that we are using, is a physics associated to a quantum process. And how can we do that? In our example, so we do the measurements of the Bell inequality violation. So here, when we are violating the Bell inequality, which is proved by the theory, so we know that we are in a situation where quantum mechanics is describing what we are observing. And there we are sure that the effect that we are observing is based on the quantum mechanics. So this is the idea.
Thank you, sir.
Okay.
Anyone else wants to ask any question?
Okay, so we'll proceed for lunch now.